Hello, welcome, and thanks very much for joining this webinar. In the next 45 minutes or so, members of the South Pole Telescope collaboration will present some new, very exciting results. These results are described in great detail in a paper that we will make available on the SPT website today and that will appear on the archive tomorrow, titled SPT-3G D1 CMB temperature and polarization power spectra and cosmology from 2019 and 2020 observations of the SPT-3G Main field. And you can see here the URL where the paper and data products will be available. My name is Tom Crawford. I'm a research professor at the University of Chicago and the deputy director of the SPT project. I've worked on SPT for over 20 years, including helping to build the telescope at the South Pole, and I am very gratified to see these fantastic new results. To give a quick outline of what you'll hear in this webinar, obviously this is me giving the introduction, then we will hear from a number of people who really did the work, describing the various aspects of the paper. First, you'll hear from Wei Xuan, a postdoc at Argonne National Labs, describing the maps and how they were made from the raw data. Then Etienne Campuis, a postdoc at IAP in Paris, will describe the maps to power spectrum pipeline and the likelihood and validation. Then we'll hear from Fei Ge, a postdoc at Stanford SLAC, on the CMB lensing information that we've published earlier from SPT-3G that we will include in the cosmological constraints in this result. Then we'll hear a couple of presentations on those cosmological constraints. First, Ali Rida Khalife, also a postdoc at IAP, will talk about Lambda CDM and extended model constraints from CMB alone. And then Leonard Balkenhol, also postdoc at IAP, will talk about extended models from the combination of CMB and DESI BAO data. Then we'll hear from Federica Guidi, also a postdoc at IAP, on upcoming SPT-3G analyses and data sets that will even strengthen further the cosmological constraints. And finally, we will get a summing up from Silvia Galli, the leader of the IAP pack. So first, let me present the SPT-3G collaboration. It's roughly 100 members, over 60 of them students and postdocs from around 30 institutions. Some of the main institutions that are involved in the result that you'll hear about today are shown here, but there are many others. And we want to give a special shout out to our supporting agencies. We are funded in the US by the NSF and the Department of Energy. We get huge support from the US Antarctic program for the logistics running of the telescope. And in Europe, we are supported significantly by the European Research Council. And none of this would be possible without all of these the support from all of these agencies. We thank them very much. A little bit of history on the SPT. We built the telescope and deployed the first camera in 2007. That was the SPT-SZ camera. Had roughly 1,000 detectors in 3 bands, total intensity only. Then we expanded the capability of SPT to polarization in 2012 with SPT-Pol. And then in 2017, we made a major leap forward with the SPT-3G camera, which was a 10-fold increase in the number of detectors and hence the mapping speed. And that is the camera that is still currently on the telescope and is provided the data from which was the basis of the result we will describe today. And now I'm going to turn it over to Wei Xuan, who's going to talk about the maps.
Okay, thank you, Tom. So I will talk about a new data set from SPT-3G and the new maps we made from that data set. So the new data set, which we are calling SPT-3G D1, this is from observations taken during the 2019 and 2020 Austro winter observing seasons on the SPT-3G main field, which is shown as this green patch in this footprint figure. We've also observed other fields, the summer-wide with SPT-3G, which you will hear more about toward the end of the webinar. This figure also shows the Planck galactic mask and ACT DR6 footprint. So I want to highlight two noteworthy facts about SPT-3G D1. So this new dataset is much larger than our previous dataset, which was based on observations taken in 2018, also on the main field. So the new dataset has roughly twice as many detectors and roughly 4 times as much observing time as the 2018 dataset. Another important point about this dataset is that it's from a small and deep survey that complements cosmological surveys conducted by the Planck satellite and the ground-based Atacama Cosmology Telescope Act. The table in this bottom right corner compares three datasets in terms of the observed sky fraction and the co-added white noise level. So from Planck PR3 to ACT DR6 to SPT-3G D1, the observed sky fraction goes down from 100 to 45 to 4, and the co-added noise level goes down from 35 to 10 to 3.3 microkelvin arc minute. So one of the key results from this webinar is that from this new dataset, we've made deepest CMB maps at arc-minute resolution used for the TT, TE, and EE power spectrum measurements and the gravitational lensing. So now I want to talk about production and validation of new maps that we've made from the new dataset. So I want to highlight some noteworthy points about these maps. So first, as usual for SPT analysis, we use the filter and Bain approach of map making to convert time stream samples to map pixel values. So we applied high-pass filters to time streams to remove large angular scale information below L of 300, and we bent the time streams to hill pix inside 8192 pixels so that we could do curved sky power spectrum estimation pipeline on our maps. After we made these maps, we applied a series of calibration and cleaning steps to the maps. This was to correct for inaccuracies in detector properties that we specified in the map making. So during map making, we specified use nominal values for certain detector properties, and we planned to correct for the collective effects of inaccuracies in detector properties across the whole detector array at the level of maps. So the properties in question are gain, polarization angle, and polarization efficiency of detector. So we calibrated these at the map level. And third, from the maps we made, we conducted a collection of null tests to probe systematic errors. In a null test, we split the full dataset into two halves in such a way that one half is more susceptible to a potential source of systematic error. And then we difference maps from the two halves to remove the CMB, and then see if the residuals are consistent with our expectations within noise or have some excess. So we did 6 types of splits. There is sun above horizon versus below, same for moon, and then 180-degree range of telescope azimuth that contains a nearby building versus the other half azimuth, and 2019 versus 2020, left-going telescope scans versus right-going scans, and one group of wafer detector wafers versus the other. So from these tests, we detected excess power above noise in azimuth and ear tests, but the amplitudes of the excess power were still well below our expected total uncertainties in our power spectrum measurements, which are dominated by the CMB signal sample variance rather than our very low noise level. We also detected large narrow band contamination at around L of 600 in scanned wafer tests, which is mitigated by harmonic space masking when we estimate power spectra. So now, having described these maps, I'd like to show a comparison among 3 sets of Stokes parameter Q and U polarization maps. So I will be comparing Planck 143 gigahertz and ACT 150 gigahertz and SPT-3G 150 gigahertz, D1 150 gigahertz. So I'll be showing a small patch, roughly 12 by 13 degrees, and you can find more details of what I'm showing in these bullet points. So this animation cycles through Planck, ACT, and SPT. So we can see that the characteristic crisscross patterns in the Q and U maps are not imaged very well in Planck maps because of the higher noise level, but the patterns are imaged very clearly in ACT and SPT maps. And because of our high-pass filter, you can see going from ACT to SPT, certain large angular scale modes are removed. And in addition, because of our low noise level, certain noisy areas in ACT, you can see gets imaged more cleanly with SPT's lower noise level. Okay, so finally, I want to talk about publications and data release associated with SPT-3G D1. So first, these are, I want to highlight these two papers that were published recently. There is Ge et al., which you will hear more about later in this webinar. And there's also Zebrowski et al., which is analysis constraining inflationary gravitational waves. So in this analysis, we use the map making setting that's different from the maps I've just shown, but the data set is the same, the 2 years from SPT-3G 2019, 2020. And then as Tom said at the beginning, the paper available today is this paper, Campos et al. And then we are making power spectrum likelihood presented in the paper available. And finally, we have 3 papers currently in progress. I am working on a paper describing map making, calibration, null tests. And then there's a paper led by Nicholas Huan talking about beams, and then by Ehik Yvonne talking about transfer functions. And we will release maps and ancillary products this year. So now I will pass the mic to Etienne, who will talk about power spectrum likelihood and validation from these maps.
Thank you, Wei. I will now present the power spectrum measurement, the likelihood, and its validation. As Wei was saying, we are using the deepest map to be used in a TT-TE analysis. On the left of that plot, I'm showing the TT noise band powers, and on the right, I'm showing the EE noise band powers. In red is highlighted the co-added white noise levels of 3.3 microkelvin arc minute in temperature and 5.1 in polarization. Hence, the SPT-3G D1 data is signal dominated in polarization until L of 2500. To deal with this high sensitivity, we had to improve our maps to band-Bowers pipeline, and we introduced 3 key developments. First, the modeling of the transfer function, then the modeling of the beams, and then Inpainting. The first improvement is the modeling of the filtering. Because we are observing from the ground, our data is contaminated by atmosphere, and we remove the large scales of the maps along the scan direction, illustrated by that brown arrow. The resulting maps are biased, as well as the measured power spectrum. We use 2000 fast and new simulations to measure the transfer function, with which we model the mode loss at the power spectrum level. And we measure that transfer function with very high accuracy. Showing an example on the right here, the TT 150-150 transfer function. The low L dip is due to the harmonic space masking we apply to remove a noise line. Otherwise, we are losing part of our large-scale modes, but we are keeping most of our small scales. Using 2000 fast simulations, we are able to measure that with very high accuracy. Next is our improved beam modeling. Our beams are separated into 3 main components. First, we have the temperature beams, which is the response in temperature to a temperature signal. We measure them from stitch point sources and planet observations with less than 0.2% accuracy. On the right, I'm showing the temperature beam at 150 in harmonic space. Next are our polarized beams, which are the response in polarization to a polarized signal. We have a new modeling for our polarized beams. We start from the temperature beam, which we split into a main beam and a side lobe beam. The side lobe beam captures the non-triviality of the beams, and we assume that the polarization efficiency of the beams can be low of the side lobe beams can be lower than the main beam polarization efficiency. These new parameters can vary, and we go from the blue line to the orange line as it changes. Since we cannot measure it from external tracers, we leave that parameter free in the likelihood, and we believe it's a conservative choice. Next are our leakage beams, which are the response in polarization to a temperature signal. We see that in stacked Q and U point source maps in the first line of that plot, where we expect the signal to be zero, but actually, because we remove monopole leakage and the sources are not polarized, but actually we see a clear quadrupolar pattern that we can model on the second line of that plot and propagate to band powers on the right. We see the contamination in TE and EE. The TE contamination is 1% of the signal at the large scales, but we mostly see it at the small scales because the error bars are relatively smaller. And we can see the contamination in EE, which is 1% of the signal at the intermediate scales. The last improvement is the use of inpainting. This is the first use of an inpainting code in a TT-TE analysis. Inpainting allows us to fill the missing data with Gaussian constraint realization. The reason we do so is that because of our high sensitivity, we are masking 100 times more emissive sources and clusters per unit area than Planck. And to avoid the increased correlation between band power modes, we actually inpaint our maps. Our inpainting code is accurate and leaves only small residual bias in the band powers. So from the inpainted maps, we can measure the band powers. We first validate the band powers before using them in a cosmological analysis using blind null test. We have 66 difference tests and 18 co-initial tests. The difference tests are just the comparison of the band powers in two different frequencies. For instance, in the middle panel here, I'm showing the EE 150 minus 95 150 difference test. On the top panel, I'm showing the error bars. The orange line is this difference test error bar that can be compared to the actual band powers error bar in blue. That test probes systematics that are 10% of the band powers error bar on the large scales. We also perform co-initial test, which uses the information from all other frequencies to predict one given frequency. The example here is EE 150 with the associated PT on the top right. The error bar of the co-initial test is much tighter than the difference test, and we can probe systematic effects which are 1% of the band powers error bar on the large scales. The SPT-3G D1 band powers pass all of our null tests. So now that I presented the validation of the band powers, I can show the band powers. I start from the state-of-the-art TT, TE, and EE measurement of the Planck in green and ACT collaboration in orange in that plot. And here are the SPT-3G D1 band powers. You can see that there is excellent agreement between the three experiments, but SPT-3G D1 data is very good at probing the small scales of TE on the bottom right panel and the small scales of EE. This is better understood in terms of signal to noise. Keep in mind that Planck and ACT observe wider sky fractions, whereas SPT-3G has higher resolution and lower noise levels. On the right of that plot, I'm showing the signal to noise ratio for TE and EE. Planck and ACT dominate on the large scales, but SPT-3G probes better the small scales. The D1 data has the tightest band power measurement in TE at L above 2200 and the EE at L above 1800 until 4000. Now that we have band powers, we can build a likelihood. The likelihood allows us to compare the data to the model. Here, I will just showcase the components, but more details can be found in the paper. We are using a foreground and nuisance model improved over our previous release, SPT-3G 2018. For the CMB theory part, we are using either Boltzmann solvers or emulators, such as Cosmo Power Jacks or Lay. The cohorts matrix is obtained based on a semi-identical framework developed in a previous work. and we implement the likelihood in Candle. Candle is a Python-based CMB likelihood framework with which we can exploit Jack's automatic differentiation algorithm to actually power a lot of null tests and additional tests in your likelihood. Now that we have a likelihood, we can validate it in a blind way. We first check that on 100 simulations, we recover the input Cosmo parameters within expectations, and this is what I show on the right, where we recover the input parameters within expectation. And also, we perform a lot of Lambda CDM parameter interfrequency null tests. We unblinded the results when we passed all null tests. After unblinding, we added two components to our data model. First, the quadrupole beam leakage, which, as I shown earlier, is very clearly seen in stacked point sources of our maps. And then next is the polarized beams. The polarized beams allow us to have better consistency of our EE band powers on the large scales. We found cosmology-independent evidence for including them, and we believe that they give a better description of our data. The likelihood will be released on the official SPT website, along with tutorial notebooks and sampler templates. Now we show our results. What we find is that Lambda CDM is a very good fit to the SPT-3G D1 data. The right of the plot, I'm showing the TT, TE, and EE band powers, along with the Lambda CDM best fit. The residuals are in the odd panels. What you can see is Lambda CDM is a very good fit. The associated PT of the TT-EE combination, the PT is 52%, and for individual TT, TE, and EE channels, the PTs are 84, 51, and 38% respectively. Here I'm showing the Lambda CDM constraints of TT in green. Then I add the EE constraints, which are tighter than TT. TE and EE Lambda CDM parameters agree within expectations. TE is actually our most constraining channel and agree with both TT and EE. The TE and EE constraints are very tight, and actually they drive the total combination of the data in dark here, which are TT, TE, EE constraints combined together. Keep in mind that including lensing will yield tighter constraints, as Faye will show later. So this is a remarkable achievement for Lambda CDM. And what we also find is that the Lambda CDM parameters are in agreement on different range scales. We split our data into three parts. First, multiples below 1000, then multiples between 1000 and 2000, then multiples above 2000. What we find is that the measured Lambda CDM parameters are in very good agreement, and this is a remarkable achievement for Lambda CDM. So let me wrap up just this section about power spectrum and validation. The D1 data is signal dominated in polarization until L of 3500. Our band powers pass all of our null tests. They provide the tightest measurement of TE at L above 2200 and EE at L above 1800. Lambda CDM is a very good fit to the D1 data for TT, TE, EE individually and all together. And finally, Lambda CDM is consistent across our frequency channels and also across angular scales. I will now leave it to Faye that will present the CMB lensing measurement from MUSE.
Thanks, Etienne. So I'm going to talk about the CMB lensing used in this analysis. So basically, we have a CMB lensing results published in last November, and those CMB lensing reconstructed band powers will be used in this analysis. So the CMB lensing data was actually inferred from the CMB polarization maps, which were introduced by Wei earlier, by using a novel estimator, which is called the marginal unbiased rule estimator, MUSE. So the inferred lensing band powers are the most precisely measured to date at L larger than 350, and also the overall lensing signal to noise ratio is at 38 sigma level. So here in the plot on the right, I'm showing the reconstructed the CMB lensing band power from the MUSE analysis in black arrow bars. And the orange and gray bands are the 1 sigma chains from the fit from SPT a 3G TTTEE plus lensing likelihood in the Lambda CDM model, as well as those using the Planck likelihood. And of course, before combining the TTT likelihood from SPT-3G with the lensing likelihood, we've already verified the consistency between these two on cosmological parameters. So a very brief introduction of the MUSE estimator. So this is an estimator which can jointly estimate the CMB lensing band powers, the unlensed CMB band powers, which is EE band powers in this case, as well as the systematic parameters. So it is a map level inference method which can effectively use all the endpoint statistics to reconstruct the lensing band powers and estimate the CMB band powers. So here on the plot on the right, I'm showing the full covariance estimated from the MUSE estimator. As you can see, we have the A55 for 55 band powers, E band powers, as well as the systematic parameters. And it is easy to marginalize over the uncertainties of the underlying CMB as well as the systematic parameters to get the marginalized covariance of the 55 band powers to combine with primary CMB likelihood. And also our reconstruction is almost cosmology independent because within each beam we don't assume, and we basically don't assume any cosmology, but just vary the band powers within each given beam. So for more details, please refer to the MUSE paper we've published in November. So for this lensing reconstruction analysis, we've also had a blinding procedure, and we've tested all the pipelines by passing all the validation tests. So here in the plot, I'm showing one of them, which is comparing the mean of the 55 band powers estimated from a set of 100 marks and check the difference between those to the input truth. So basically, if the delta A55 is 0, which means we recovered the input truth. So here the color line shows the same test by using either the single frequency maps or combining all three frequency maps in the red. So as you can see, we basically recovered the input truth, and our pipeline is unblinded. It's unbiased. And then we also checked the consistency of our reconstructed lensing band powers with Planck Npipe results as well as the ACT DR6 results, of course, after we unblinded. And those you can see. So you can see in the plot on the right. So the color boxes are the individual lensing measurements. So SPT-3G MUSE results are shown in blue boxes, and the ACT DR6 and Planck PR4 are showing in pink and yellow boxes individually. And we also have a joint analysis by combining the SPT, Planck, and ACT lensing reconstruction altogether, which yields a 61 sigma signal to noise ratio level measurements of the CMB lensing amplitude, which is 50% increase of the individual lensing measurements. And also in the joint analysis, we also show that the correlation between the SPT and ACT or Planck lensing is less than 10%, which and so then I will hand it over to Ollie, and he will talk about the cosmological constraints by combining the primary CMB likelihood as well as the CMB lensing.
Thank you, Faye. Before presenting constraints on Lambda CDM and its extensions from the CMB, let me briefly go through the different datasets that we consider. First, as mentioned by Wei, we define SPT-3G D1, where D1 corresponds to the observations of the main field in 2019 and 2020, the results of this work, including primary CMB data and the lensing band powers from the MUSE analysis that Faye just described. We define a Planck dataset that includes Planck PR3 data in temperature and in polarization at high multipoles, in temperature at low multipoles, and the lensing band power from the PR4 maps. We combine SPT and ACT, both in primary CMB and the lensing band powers, into a single dataset that we call it SPT plus ACT. We also look at the combination of the SPT and PACT, where PACT is the combination of Planck with the ACT data, such that the Planck data in temperature in TT at L larger than 1000 is cut, and in TE and EE is cut at L above 600. We call this combination CMB SPA. In all these datasets, we impose a prior on the optical depth to reionization tau from the Planck PR4 maps with the values presented here. Our first result is that for the first time, SPT-3G alone is able to provide constraints that are comparable to the ones from Planck within 25% on the acceleration rate to day H0 and the root mean square value of the matter fluctuations on a co-moving scale of 8 megaparsecs sigma 8. This is a remarkable achievement for a dataset that covers only 4% of the sky. We also find that SPT and Planck agree with each other at 1.1 sigma, as is also shown from the overlap of the contours here, while SPT agrees with ACT at 0.4 sigma. The agreement between these experiments has two implications. First, it indicates the robustness of the CMB science. Second, it's a formidable test for Lambda CDM. As already mentioned by Etienne, the fact that Lambda CDM is able to fit all these data sets is a major achievement for this model, given that these data sets are complementary to one another in sky coverage and in sensitivity. Next, we find that for the first time, SPT plus ACT is able to reach the Planck's precision on key Lambda CDM parameters. This is a milestone for ground-based experiments. Since Planck has dominated the world of cosmological constraints for almost 12 years, now we are entering a new era in which ground-based experiments constraints are able to surpass the ones coming from Planck on these Lambda CDM parameters. It is worth noting, actually, that SPT plus ACT constraint surpasses the one coming from Planck on these key Lambda CDM parameters. For example, if we look at sigma 8, we find that the constraint coming from SPT plus ACT is almost 18% better than the one coming from Planck. On the other hand, if we replace Planck PR3 data with CAMSPEC PR4, we find that SPT plus ACT has similar constraints to that combination. And then, when we combine all CMB data together, we provide the most precise and up-to-date constraints on Lambda CDM parameters. For example, now we have H0 to be 67.24 plus or minus 0.35. The agreement between these experiments and with the predictions of Lambda CDM allow us to present the new status of the Hubble tension. All three experiments are now confirming the presence of this tension. Remember, these are three almost completely independent experiments with compatible and complementary angular scale coverage in temperature and in polarization. From SPT alone, we find that the tension with the recently measured value of H0 from MUSE to be now at 6.2 sigma, while from SPT plus ACT and CMB SPA, this is at 6.8 and 6.4 sigma respectively. We also provide the new status of the clustering of matter. As mentioned before, SPT is able to provide a constraint on sigma 8 that is almost as well as Planck. Remember, this is coming just from 4% of the sky. We also find that different probes of the clustering of matter agree with each other in the sigma 8 omega m plane. So from CMB primary data, its lensing, a 3x 2-point analysis from DES, or the abundance of clusters identified by SPT, they all agree with each other to a very good degree, and also with the cosmic shear results from the KIDS legacy. And now we have the most precise and up-to-date constraint on sigma 8 and omega m coming from CMB data alone. Finally, we extend Lambda CDM with a variety of parameters, starting with the lensing amplitude, the amplitude of the lensing power spectrum A2 point. This is motivated by the lensing excess that was found in the Planck data, where that data seems to prefer a slightly higher amplitude of this parameter compared to predictions of Lambda CDM. Now, with SPT and SPT plus ACT, we do not find this to be the case. In addition to these datasets to be in agreement with each other, they are also in agreement with the predictions of Lambda CDM. And they give a lower value from the one that is constrained in Planck at the order of 2 sigma. We also extend Lambda CDM with the sum of neutrino masses and find that the inclusion of SPT plus ACT on top of Planck reduces the upper limit on the sum of neutrino masses by around 30%. This is again showing the constraining power of SPT plus ACT. We also extend Lambda CDM with additional relativistic species quantified by their number NF, and or with a variation of the primordial helium fraction YP, or with modified recombination history. As an example of these extensions, we show the most up-to-date and precise constraint on NF coming from the combination of CMB data. And in all these extensions, we do not find any statistically significant deviation from Lambda CDM. And with this, I hand it over to Leonard, who will describe constraints on these models and more from CMB and BAO data.
Thank you, Ali. I'll start by presenting joint constraints from CMB and baryon acoustic oscillation data on the standard model. So we're back to Lambda CDM. The state-of-the-art BAO dataset is the latest release from the DESI collaboration. Now, before we combine datasets, we first need to ensure that they're consistent with one another to justify joint analysis. BAO data constrain the relative matter density, omega m, as well as the product of the expansion rate and the co-moving size of the sound horizon at the end of the baryon drag epoch, HRD. You can see constraints in this 2D plane. In the left panel here, we have omega m, as well as HRD. The DESI constraints are shown in gray, and the SPT result is in blue. Now, in this analysis, we require for differences in this 2D plane to be less than 3 sigma to justify a joint analysis. This is the case for SPT-3G D1 and DESI, which are different at 2.5 sigma. While this is on the high side, it's underneath our threshold, and you can find the full joint constraints in the paper. The addition of the DESI data improves notably for determinations of the scalar spectral index, NS, matter clustering as parameterized by S8 or sigma8, as well as the expansion rate, H0. Here we now achieve a precision of 0.31 kilometers per second per megaparsec, about a factor of 2 better than the SPT-only result that Ali presented a few slides ago. So SPT and DESI are consistent with one another, but this is not true for all CMB data. If we look at the latest and final release from the ACT collaboration, ACT-DS6, we find that it's different from the DESI constraint at 3.1 sigma. Similarly, the combination of SPT and ACT data with very tight error bars is different from DESI at the 3.7 sigma level. Now, it's important to bear in mind that certain analysis choices can influence this comparison, and specifically for the case of ACT data, an alternative tau prior choice can reduce the difference below the 3 sigma threshold. Still, as Ali demonstrated, CMB data is very consistent, and so we expect that as we add more of it, we should converge towards the underlying mean. And so for a combination of SPT, Planck, and ACT data, CMB SPA, we find that it's different from DESI at the 2.8 sigma level. This is underneath our threshold. While so high, you can find the joint constraints in the paper. Still, it's important to keep an eye on the differences in the matter density and HRD between DESI and CMB data. Now, this is the case in Lambda CDM, but moving beyond Lambda CDM, considering extensions, we find that these differences between CMB and DESI data can be reduced to 2 to 3 sigma deviations away from Lambda CDM. We find this for a variety of different models. You can see a full list of the model classes we consider in the paper on the slide here. On the right-hand side, I want to illustrate as an example the case of spatial curvature. It's parameterized by omega k. The standard model value here, omega k of 0, corresponds to spatial flatness. The CMB constraint from CMB SPA is shown in blue. It's consistent with the standard model prediction, less than 2 sigma. Now, adding DESI data, we move to the orange constraint here. We increase omega k. This in turn leads to a lower omega matter inferred from the CMB data, thus bringing the two probes into better agreement. The joint fit to CMB and DESI data is thus improved, and in this case, we have a preference over Lambda CDM for an open universe at the 2.5 sigma level. And we unpack these results in the paper, pointing at the degeneracy directions at play and tying it to the underlying physics. We conclude that with our current data, there's no definitive evidence for a breakdown of Lambda CDM, at least just yet. The evidence at the 3 sigma level remains moderate. It's also important to point out that these trends emerge in the joint constraints, and so far, no detection of new physics has been achieved by either probe individually. So what we're looking at may be a statistical fluctuation, or, as one always fears, perhaps a systematic issue we have not identified yet. What is clear is that more data will allow us to make a stronger judgment, to see whether these trends that we're observing are robust and perhaps the hint of new physics. SPT will continue to play a key role in delivering these insights. And our next speaker, Federica Guidi, will tell you more about the future of the experiment.
Thank you, Leonard. It's my pleasure now to give you a preview about future CMB analysis that we are performing with new data of SPT-3G. Indeed, what we have just presented is only the beginning for this experiment, because in recent years the survey has been further evolving. As a reminder, what we have presented today is from 2 seasons of observations of the main field, but we have already extended it, first of all, with the summer fields, in yellow in this figure, that are observed during the austral summer. This has been performed during 4 summer seasons between 2019 and 2023, and the sky fraction has been expanded by about 2,600 square degrees, with a noise depth of approximately 7 arcminutes, micro K arcminutes, which is 4 times better than what measured by the Planck mission. The survey has been further extended with the wide field during 2024, adding additional 6,000 square degrees with a depth of about 9 micro K arcminutes. And in the recent years, of course, we have continued observing the main field during the winter austral season for 5 years between 2019 and 2023. We are continuing these observations this year, next year, and possibly even more. And our target is to measure this sky with a noise depth of 1.6 micro K arcminute. And this will bring us plenty of results beyond what we have presented today. First of all, we will publish soon an update of our lensing analysis. This is using the same observations as in today's results, but we are using now a quadratic estimator technique, and this is based on both temperature and polarization CMB data, contrary to what we have presented here, which was based on the MUSE estimator and from polarization only data. It will follow shortly after the first release of summer fields analysis. This is an analysis in a very advanced stage based on the first 2 seasons of survey on the summer fields. And from a combination of summer and main field data, we compose what we call our X4K survey, covering 4,000 square degrees now in total. And this is 3 times more sky than what we have presented today. And we are delivering CMB primary anisotropy power spectra TT, TE, and EE, and a lensing reconstruction with 5 band powers. We have already started analyzing also the wide field data, and this in combination with the summer and main field composes our X10K survey, covering in total 10,000 square degrees, which is 7 times larger than the sky presented today. And we are measuring the CMB primary anisotropies in TT, TE, and EE, and lensing. These results will significantly boost the signal to noise of our band powers, and as you can see in the figure on the right here, and you can compare, for instance, the signal to noise of the EE power spectrum from Planck, shown in black, or the signal to noise of the same power spectrum from the main field analysis of today's results in green, and you will see how much we can improve our signal to noise, including our X4K or X10K survey. Obviously, the cosmological constraints will significantly improve, and we have published in last year, 2024, a forecast paper about what we can achieve. And for the future, of course, we will update all these analyses using full depth in the main and summer fields, and the camera will be replaced in 2029. SPT-3G Plus will take over and continue observations from the South Pole. And with this, I'll leave it to Silvia for the conclusions.
Thank you very much, Federica, and thanks to all of the speakers. As you've understood, we are extremely excited about these new results, and so I'm going to end this talk by, first of all, summarizing a bit the key results that you've already heard in this presentation. The first message that I would like to underline is that SPT-3G data are powerful. We produced the deepest maps at high resolution for TT, TE analysis with white noise levels that are about 10 times deeper than Planck. This allowed us to provide the most sensitive measurements of the EE band powers at L larger than 1800 and of the TE band powers at L larger than 2200. This data allows us to set very tight constraints on cosmological parameters, and in particular, SPT-3G data alone allows us to measure the Hubble constant, or sigma 8, with a constraining power which is comparable to Planck within 25%. And this allows us also to confirm the Hubble tension. For example, SPT-3G data alone are different from the results of the MUSE collaboration by 6.2 sigma. The second message is that Lambda CDM is an excellent fit to the SPT-3G data. We now find excellent agreement with the results of ACT and Planck. And actually, the consistency of these three experiments really shows the robustness of CMB science. SPT, ACT, and Planck are three almost independent experiments with very complementary constraining power, sky coverage, and sensitivity. And Lambda CDM fits very well all of these three experiments. The combination of all these three provides the best CMB constraints to date. And we also explored extended models of Lambda CDM from SPT-3G data alone or in combination with other CMB experiments. And we didn't find any preference for extensions of Lambda CDM. The third point is that we find it extremely interesting that the combination of ground-based experiments, in particular of SPT and ACT, finally reached Planck's precision on some parameters. Planck has dominated the field in the past more than 10 years, and we are then really on the edge of a new phase for CMB science, where we're going to learn more and more about the nature of our universe from ground-based experiments. Also, we compared our results from SPT-3G data alone or in combination with other CMB experiments with the results of coming from BAO measurements, in particular the BAO measurements from DESI. And we find that there is a disagreement between CMB data and BAO in Lambda CDM at the level of 2 to 4 sigma. We also find that extending Lambda CDM, this disagreement is relaxed. And so by combining BAO and CMB data, we find a mild, moderate preference for beyond Lambda CDM models at the 2 to 3 sigma level, for example, in the curvature of the universe, the dark energy, equation of state, the amplitude of lensing, and a few others. So only time will tell whether this is really something new that we are discovering about the universe, or it's a statistical fluctuation, or the origin is due to systematics. But the good news for SPT is that, as you have seen, this is only the beginning. We have so much more data that we collected these years, and we are already analyzing. And we hope that we will be able to update these results soon. So the results from the cosmological results that you've seen today are summarized in a paper that will be publicly available today on the SPT-3G website. And we are releasing as well our likelihood code that will allow you to reproduce the cosmological results. And we are extremely eager to discuss with you about our results. So you are very welcome to contact us or to participate in some of the conferences where we are going to present these results. And to finish, I would like to underline the fact that the results that you've seen today are really the product of the work of many, many people in the SPT-3G collaboration that worked very hard for many years to produce these results. And I also would like to thank again our funding agencies that made all of this possible. And with this, I thank you very much for attending this webinar, and we are very eager to discuss with you soon. Thank you very much.